Okay. Hello everyone. Tonight we'll be having Madhu, and he'll be talking to us about topological quantities. Madhu, yours.
Thanks.
Yeah.
Thanks. Thank you very much for this opportunity. I would like to say a few words before I begin, and that is sort of related to the general plan because it's undergone some changes over the last few days. This is after I realized that the talks were not open-ended, that they were an hour and a half. So what's going to happen now is I'm going to give 3 talks back to back, right? So this Monday and then the next 2 Mondays, and my plan is to cover in these 3 talks some aspects of topological quantum field theories, right? So there's some physics there, and also some mathematics background, and this is sort of basic geometry that some of you may or may not have seen. I've decided to err on the side of caution and just include it in case some of you are not familiar with this language. The reason for doing this is, well, there's 2 reasons. One is that I will have use of it in the coming lectures, but more importantly also is that after I finish this series of 3 lectures, Shubham is going to take over and he's going to be talking about anomalies. And a lot of these geometrical ideas are going to be very useful in understanding anomalies as well. So it sort of serves as prerequisites for both of these talks, right? And then after Shubham is done, I think I'm going to come back and then I'm going to talk about more stuff related to topological quantum field theories. So this is I guess you guys should strap in for the long haul. Yeah, as usual, please feel free to interrupt if there are any questions. Okay. The other thing that I wanted to say is that the first part of this lecture, I've actually written notes. In the second half, I'm going to do sort of off the cuff. So the quality may deteriorate over time, but the focus here is to have everyone understand what I'm saying. So please feel free to interrupt me whenever. And also at the end of it, please let me know which one you prefer, me making notes beforehand or me doing things live. Okay, so now the subject of this series of lectures is topological quantum field theory. These are a special class of quantum field theories. Oh, I have another request. If some of you could possibly keep your videos on, if you have good internet connections, or your audio on at least, that would be helpful, because then I can see some faces and it doesn't seem depressing. Thank you.
Hi.
Yeah. So anyway, what I want to, maybe I should also keep the video on. Yeah. So the subject of topological quantum field theories is an old one. It goes back about 40 years or so, maybe even older than that. And one of the things, the perspective that I would like to communicate in this series of lectures is that topological quantum field theories are to quantum field theories what integrable systems are to classical mechanics, right? In the sense that when we study classical mechanics, you just give me Newton's laws and you give me a set of initial conditions and I'm good to go, right? But very often formulating things in terms of Newton's laws is not very useful, or it's not very enlightening. What we do is we like to use more sophisticated mathematical tools to try and understand these structures better. And topological quantum field theories are kind of like that. They're a class of, they're legitimate quantum field theories, right? And they're very interesting. And the especially nice thing is that you can actually calculate things exactly. Many times you can calculate a lot of things exactly. So that's the perspective that I will be trying to communicate in this series of lectures. There exists an axiomatic formulation of topological quantum field theories that is due to Atiyah and Segal. I think we'll maybe see this next week or the week after that, depending on how this goes. But for now, what I want to do is I just want to start off easy by going for a more physical definition of TQFTs. Okay, so in quantum field theories generally, the objects of interest are correlation functions, right? So over here, hold on. Yeah. So over here, for example, I have a correlation function of some operators, right? These are typically required to be gauge invariant operators if we're talking about a gauge theory. Otherwise, just generally physical typically means gauge invariant in this context. We have physical operators and we want to compute their correlation functions, right? The subscript B here is supposed to denote a background. And when I say background, I mean any other data that you need to give me in order to define this quantum field theory. For example, what manifold is the theory being put on? Does the manifold have a metric? Is there a complex structure? Are there coupling constants? Are there background fields? Things like that. Okay. So this is the B is supposed to indicate all of these things, right? And these are the kind of objects that we are used to computing in perturbation theory, right? We know how to compute time-ordered correlation functions in ordinary perturbative quantum field theory. So these are still the objects that we will be interested. Topological quantum field theories are defined in a very specific way. You start off with a theory on a manifold M, right? It may or may not have a metric. We'll see. We'll look at that in a moment. But we start off with a theory on a manifold M, G. A quantum field theory is called topological if its correlation functions do not depend on the choice of G.
I think his internet got stuck or something.
Seems like it.
Yeah.
Seems like it.
Yeah.
His internet is not able to handle all these videos, I think.
Yeah, I think maybe a couple of you should just keep the video on.
Oh, I
Most
see.
of us
Sorry. Yeah. Okay. So what we So I was saying that like the correlation functions don't depend on the choice of metric. Okay. Now
I had a question. So
yeah,
there must be other type of observables also, like Wilson lines and so on and so forth. Are there those kind of observables? So is this definition more general that any observable in quotes will not depend on the choice of G? I mean, our correlation function is the only observable. That's part one, and part two of the question will be
well, I mean, even if we're interested in Wilson lines, the only difference is that those are like non-local operators, right? We're still computing correlation functions, right? And notice that I never said anything about, well, okay, fine, I've put the operators at a point here, but in general, you can forget these and you can just say that you have, operators that have supports on maybe a line or a surface or whatever, right? So, in general, we will be interested in computing correlation functions, right? And correlation functions may be of local operators, non-local operators, whatever. But none of these correlation functions should depend on the choice of the metric. Okay. The key point here to remember is that we are not introducing a metric and then integrating over all the possible metrics that you can put on this manifold. Okay. The metric is a background in this game. The point is that if I have a manifold M and I give you two, let's say any two metrics, G and G prime, right? Then the correlation function doesn't care about whether you put G on the manifold or G prime on the manifold. That's the point. We're not integrating over the metric in the path integral. If we start off with the TQFT and then we make the metric dynamical, that's when we start talking about things like topological strings, which is not the subject of this series of lectures. We can talk about that later on, of course. The second thing to keep in mind is that TQFTs are not just sensitive to the topology of M. Okay, they can depend on other background information, like for example, the choice of a complex structure. In fact, we will see that in the sort of paradigmatic examples of TQFTs, certain class of TQFTs, there will be dependence on complex structure or Kähler structure or something like that. None of this requires a metric to define, but the point here to remember is that when we say TQFTs, we don't just mean that it is only sensitive to the topology of the manifold. There may be other things also, just not the metric. Okay. So this metric independence is very simply stated in the following way. Okay. We just have a correlation function, the one that I wrote down earlier, and there is some background. And I just say that like when I vary the metric, this correlation function does not change. Okay. Now, the simplest way to do this, of course, is to construct a theory that makes no reference to the metric at all. If you're able to write down the Lagrangian of a theory and the Lagrangian density of a theory, and that Lagrangian density does not require that we specify a metric, then we've finished, we're done, right? And these are what are called Schwartz type topological quantum field theories. Okay, there is another kind of topological quantum field theory, the kind that does not require the metric to construct, is called a Schwartz type topological quantum field theory. The prototypical example of this is what is called a Churn-Simons theory, which I'm sure all of you have heard of. Churn-Simons theories, you know that the action for Churn-Simons theory looks like you have a gauge field A, right? And this is A dA plus 2/3 A cube, right? Now this Lagrangian density does not require a metric to define, right? You just need differential forms on this manifold. So we will talk about Churn-Simons theory, some basic aspects of Churn-Simons theory, I think probably in the third lecture, right? But what I'd like to do today is I'd like to pick up the harder task, which is to start with a theory that has a metric, right? And still construct it. So you can imagine that the harder thing to do would be to start off with a theory that requires a metric to define, and then still show that this theory doesn't, the correlation functions don't depend on the metric. That seems like the harder thing to do. And that's precisely what we're going to study next. Are there any questions at this point? Okay, so, sorry, was there a question? Okay, so the non-trivial task is to start off with a theory whose definition requires a metric, but it is still a topological quantum field theory. These are called co-homological or Witten type TQFTs. Okay, so let's do some, let's try and recall some basic stuff. We consider quantum field theory, classical field theories. Noether's theorem tells us that continuous global symmetries are associated to conserved charges. Okay, this is the statement from classical field theory. In the corresponding quantum field theory, this conserved charge is the generator of symmetry transformations. So if I have an operator O, right, this operator may have bosonic or fermionic statistics, an infinitesimal variation with respect to this symmetry is given by the commutator of the charge S. S is the charge, the commutator of S with O. Okay, and these brackets denote commutators or anti-commutators depending on whether the symmetry is bosonic or fermionic, and whether the operator is bosonic. Now, typically when we have a symmetry in our problem, the states of the theory, the physical states, are organized into representations of that symmetry, right? So symmetry invariant states are those that are annihilated by the symmetry generator. Okay? And in particular, if the vacuum is not if the symmetry is not spontaneously broken, then S annihilates the vacuum. Okay. Now, the point here is that operator expectation values are then invariant. So how do we see that? We start off with a correlation function, let's say O, OI, O, right? That's a vacuum correlation function, a one-point function of some operator. Or this it could also be a string, it doesn't matter. And what we do is we perform an infinitesimal variation. Right? Then we use the fact that the symmetry is generated by the charge, and we are able to write down something like this. So we have just the original guy, and this is the delta epsilon O, right? But now we can use the fact that if the symmetry is not spontaneously broken, we can use the fact that S annihilates the vacuum, and we get the same thing that we started out with, right? So now let's play the same game, but with some arbitrary state psi. Okay, I play the same game with some arbitrary state psi. Observe that this term, the order epsilon term here, right? Order epsilon which is the leading order in the variation, infinitesimal variation. We can get the second term just by sending psi to psi plus I epsilon S acting on psi. Okay, if S were the Hamiltonian and we were talking about time evolution, right, then this would just be the transition from the Schrodinger to the Heisenberg picture, right? Where in one case you have, in the Schrodinger picture, you have the states evolving in time, right? And in the other picture you have the states fixed and the operators evolving in time. Okay, good. The point is that there's already something cohomological about this. Okay, what we're saying is that if we can get, for some state psi, if we can get the second term just by performing a shift like this, then in some sense the state psi and the state psi plus S times psi, S acting on psi, are equivalent, right? Because they give you the same, when we compute correlation functions, they give us the same answer. So a cohomological field theory is something that makes this precise. And it does so using a number of axioms, which I will list now.
Can you repeat that? I didn't quite follow.
Yeah, the last part I did
argument.
not get.
Yeah.
Yeah.
So the point I'm trying to make is that if I consider the variation of a correlation function under a particular symmetry transformation, okay, and I find that since the S annihilates the vacuum, that the correlation functions are invariant. Okay. Now and all of this was happening in which picture? It was happening in the. I mean, it's not correct to say Schrodinger and Heisenberg, but let's call this the Heisenberg picture. Okay? The reason I'm calling this the Heisenberg picture is because the operators are the ones that are changing. Okay. Now what I'm doing is I'm saying that let's play this. We can get the same kind of term, right, by just changing the states, leaving the operator the same and changing the states. We get the same kind of term, right? And what we find is that the state psi is in some sense equivalent to the state psi plus I epsilon S acting on psi.
But does the symmetry also annihilate psi? Is that an assumption?
No. I mean, this is just so sorry. Maybe I should have clarified. This is just an analogy that the idea that like you have states that are kind of equivalent to each other. I'm just trying to sort of build an analogy here.
I see. Okay.
Okay.
S square is also not 0 so far, right?
Yeah. I haven't required that S squares to 0 yet. We'll get there, right?
Okay.
But at this point, this is just an analogy. But if this is confusing to people, then we can move on. I can just give you the axioms.
Yeah. I think maybe instead of Schrodinger, Heisenberg, maybe it would be better to say like active or passive in that sense. Right?
Oh, okay. Yeah. Right.
Something like that.
That would probably be better way of saying it. Yeah.
Hello.
Yeah.
I want to ask that this psi, you wanted to say that instead of transforming the O, you can transform the psi so that you will get the same result. But for the psi, do we expect that this expectation is invariant under this epsilon transformation?
No, we don't. I'm just
okay. That's what I think was.
Yeah. I'm just trying to sort of make an analogy.
Yeah, that is true. That analogy is correct, but the same term will not go to 0 in the psi case.
Yeah, for an arbitrary state. Yeah.
It have to be linear combination of the J, as you said previously.
Yeah. The symmetry invariant.
Symmetry invariant states. Yes.
Yeah. Okay. Cool. So let's maybe it's better to just move on. Let's just talk about what the properties of a cohomological field theory are. Okay. We'll understand why we say cohomological in just a minute. Okay. So the requirements of a cohomological field theory are the following. There exists a fermionic symmetry operator Q that is nilpotent, right? When I say nilpotent, what I mean is that Q squares to 0. Okay. The second requirement is that physical operators are closed under the action of Q. What that means is that, when I take the commutator of Q with any physical operator, I should get 0. Right? In some sense, this is the definition of a physical operator. Right? Or well, almost. Q symmetry is not spontaneously broken. So Q has to annihilate the vacuum. Okay. The symmetry Q, the fermionic symmetry that we introduced, it has to annihilate the vacuum. Now, this is the interesting point, that when I require that Q symmetry is not spontaneously broken, so this annihilates the vacuum, what this implies is that the operator OI, any operator OI, physical operator, is equivalent to OI plus Q acting on some lambda, some other operator. The reason for this is that, as you can easily check, if I act with Q on this, if I do this, then I have to do Q acting on both these terms, right? And Q squares to 0, so this guy goes to 0, right? So the point is that you can plug this equivalence into a correlation function, and the extra term, and you'll have an extra term coming from this guy, right? So let's say I have a string of operators O1, O2, On, right? Now what I do is I plug in this equivalence relation into a correlator like that. So basically, I'm going to get what I started out with, plus I'm going to get a term like this: O1, O2, Q, lambda, O3, On, right? I'm going to get something that looks like that. And when I get something like that, what I can do is I can write out the commutator in full, and then I can commute the Q all the way past all of the other operators, all of the other physical operators, and then have it go hit the vacuum. The fact that I can commute it past the other Qs is because of this requirement, right? So, and all that I'm going to do is I'm going to pick up signs. I'm going to pick up +1, -1, stuff like that, okay? But the point is that I can commute the Q past all of the other operators, and I can have it hit the vacuum, and so that term goes away. So the point is that you can move Q past the other operators and hit the vacuum, and so this extra piece does not contribute to the correlation function anyway. So what we're saying is that physical operators are in what are called Q cohomology classes. Okay. What is a Q cohomology class? A Q cohomology class is basically the statement, the requirement that all my is basically these two conditions, is defined by these two conditions. It says that Q has to commute with the operator, and also that the operator plus Q acting on anything else is equivalent to the operator. So the space of operators gets cut up into these pieces. Okay. And the fact that physical operators are Q cohomology classes is precisely why these are called cohomological field theories. Okay. The final requirement is that the stress tensor is Q exact. Okay. So when I say that the stress tensor is Q exact, what I mean is this is the usual definition of the stress tensor, right? The stress tensor is the variation of the action with respect to the metric. And what so clearly what's happening is there is a metric in this game, right? I haven't said anything about the theory, the Lagrangian or anything like that, but there is a metric in the game. The theory has a stress tensor, and the point is that P alpha beta, the stress tensor, has to be Q exact. When I say Q exact, I mean it has to be Q of something, and that something here is what I will call GAB, G alpha beta. Okay. Now this requirement is kind of crucial. It might seem a little arbitrary at the moment, right? And if those of you who are wondering where I'm coming out with this, we will see that kind of post facto, this is a reasonable thing to assume.
So you are saying any OI which can be written as Q comma lambda is called Q exact.
Yeah. So okay. So let's get the terminology. So when I say, let me write this properly. So this condition is called Q closed.
Yes.
Okay. So if the operator is in the kernel of Q, which means that when Q hits the operator, then it's 0, then it's called Q closed. If any operator, if there is an operator OI, sorry, let's write it like this. Let's write it as let's say theta is equal to Q acting on lambda. Theta is Q exact. Okay, that's the definition. So the whole point that physical operators are Q cohomology classes is the statement that you take the space of Q closed operators and then you mod out, you have an equivalence relation by the Q exact guys.
So also Q exact operators will be Q closed, but is the inverse true? I cannot see immediately.
No, the inverse is not necessarily true. That's a very good point. The fact that Q squares to 0, right, tells you that an operator that is Q exact is automatically Q closed. Okay, but a Q closed operator need not be Q exact.
Okay.
Okay, and that's precisely, and so this is an important point. That's precisely why there is a non-trivial space of physical operators. If everything that was Q closed was Q exact, right, then you would not have any non-trivial physical operators. Your correlation functions would all be 0.
Yeah.
Right? Shubham, did you have a question?
I just want, yeah, I think you answered my question. I wanted to ask about the stress tensor correlator, like correlator of stress tensor with other operators, physical operators in the spectrum, that's always 0, right?
Yeah. Yeah, because of this,
Because
right?
of this,
It's the same argument that you just plug it in and then you just commute it past everything. Okay. Good. Now, so this requirement is kind of crucial. Okay, and we'll see why it's crucial. We'll see exactly what this buys us. What it buys us is the following: we can show explicitly that our correlation functions are metric independent. Okay. Now, how do we do that? What we do is we start off with just the correlation function. You defined in the usual way as some path integral. Okay. Here phi is just denote some collection of fields. OI are the operators, and I'm going to vary it with respect to the metric. Okay. Now I've assumed that the operators themselves do not depend on the metric. Okay. Which allows me to say that the next line, basically this guy is just going to go straight and hit S, which gives me this piece. Right. But now, so this is just a stress tensor, and the stress tensor we know by our assumption, by our axiom, the stress tensor is Q exact. So it's Q acting on G alpha beta, right? And so now this whole guy over here can be written like this. There's O1 to On, and then I have Q G alpha beta. Okay, and we know that, yeah.
Can't O1 have derivatives on it, like covariant derivatives? Why you are saying that O1 is independent of H alpha beta?
This is an assumption that I'm making.
Oh, okay.
Yeah.
Okay. Yes.
So good. So what we've been able to show, and you see that like this is why the stress tensor being Q exact is a very important requirement. You see that we can show that all these correlation functions are identically zero. Sorry, not correlation functions are identically zero. The variation of the correlation function with respect to the metric are zero, which means the correlation functions are metric independent. Okay. Now you'll notice, of course, that I've done some messing around here. What you should do is you should really, I mean, in usual quantum field theory, like this when we write down a string of operators like this inside that, what we typically mean is that they're computing time-ordered correlation functions. Okay, so I've not written the big P here. Okay, and what that means is, of course, that when I bring this guy down, then I should really be putting like a time-ordered symbol. But the point is that in a topological quantum field theory, the positions where the operators are inserted don't really matter so much. And the reason for that is that because there's metric independence, what I can do is I can move the operators around however I want. Because in some sense, the fact that the fact that it's independent of the metric, right, tells us that the somehow this is just intuitively one can make this more precise, but this is just to give you an idea. Somehow the distance between the operators doesn't matter so much. It's just whether the operator is there in the correlator or not. And that's why I haven't bothered to write down the time ordering and all that. Sorry, there's a question.
Agnish, you want to ask first? I had something to ask, but I think you also wanted to ask.
Yeah. I was just this statement that it doesn't matter what the position is of the operators. I mean, if you have topological abstractions, like I could have like a cylindrical hole or something. I mean, then it matters, right? I mean, whether both operators are on one side or the other side.
So the thing is that the question, I guess, can I ask you a question slightly differently? Are you asking that like if the manifold on which the theory is defined has some non-trivial topology, right? Isn't it going to be sensitive to that?
Yes, I mean, with regard to the point that you made, that it doesn't matter where I mean, the location of the operators. I mean,
right.
So if I have the topological abstraction clearly giving me, a time after this and a time before this.
Well, I mean, we can't really. We'll see that like the notion of time itself is a bit is not very well defined here, in the sense that like it's not exactly clear. It's not exactly clear how to say one operator came before the other and stuff like that. But my point is that if your question is the correlation function sensitive to the fact that there are holes in the manifold or something like that, absolutely yes. Okay. That's something that the correlation function is definitely going to pick up on.
Okay, I wanted to ask this one naive thing. You said that Q squares to 0. By that, do you mean the action of Q on the OI, in the sense that bracket Q bracket Q O is 0, or do you mean that Q square?
Oh no,
itself?
I mean the action of Q. Yeah.
Yeah, you don't mean Q square, because Q square could be H. Like I mean your T itself
Yeah,
could be
sorry.
like Q times Q.
Yeah, no. I when I say Q square, I mean when it acts on, right? When I say this, what I mean is, yeah, exactly what you said.
Okay, you don't mean that Q square itself is a vanishing object.
Well, I mean, so the thing is that when you mentioned that Q square is H or something like that, right?
Yeah.
So the what you're referring to, of course, is the fact that we do know of a global fermionic symmetry that has all of these properties, that has physical states organized into representations of the Q cohomology, right? Which is precisely the supersymmetry when Q is a global supersymmetry.
Right.
But the point is that even over there, the Q itself, right? Each of the individual Qs, they do square to 0, right? Which is why you have a finite multiplet.
I see.
Right. When you're saying that, when you say that like Q squares to like the Hamiltonian or something like that, what we really mean is that Q1, Q2 or something like that.
Right.
We don't really, because if I have Q1 square, then that's going to like that is going to vanish.
Right. Okay.
So yeah, but I mean, for the purposes of this discussion,
it's an odd object after all. Yeah.
Yeah. So, but for the purposes of this discussion, right? For the moment, all I will mean is we will look at the supersymmetry case in more detail, but all I mean right now is just this.
Okay. Thanks.
In the same way in which, for example, if you're studying like the de Rham cohomology or something, right, then the exterior derivative squares to 0. What I mean by that is that when I act with it twice, then I can prove that because of the anti-symmetry, this guy vanishes.
Okay.
Okay. Are there any other questions?
Madhu, so as you said in this correlation functions, they don't depend on where where you're placing the operators.
Yeah.
So if I fix the topology, does it mean that like correlation function is always some constant number? Because like then what is it a function of? Generally, correlation functions are functions of distance, right? So here, what would it be?
Well, I mean, so you can still have a number of things, right? You can have, for example, you can have, they will typically be numbers, but those numbers mean something from the point of view of the TQFT. Like they represent like 2-point functions or something like that. Like,
oh, okay.
We will see. We'll see these objects. The idea that like we will have 2-point functions. We will get there. We'll actually explicitly compute correlation functions.
Okay. I mean, it could be only a function of some topological invariance, right?
Well,
maybe let me not go there.
Yeah, let's not say things like that yet. We'll see how it goes, right? But there are things. There are numbers associated with the theory, and those numbers are the ones that are going to show up.
Okay.
Yeah. So I also had a question. So the derivation that is right now on the screen, the correlation function being invariant under variations of the metric, this is strictly for theories with a non-dynamical metric or with a fixed background metric. Like for example, 3D gravity could not be written as a homological TQFT. Is that true? I mean, is that?
Well, so the part of the specification I mentioned was that gravity is not a dynamical field in this game.
Okay.
So yes, that's correct. Okay. Good. All right. So cool. So let's. So I've given you 4 properties. Okay, and these 4 properties are kind of nice, right? We saw that Q squares to 0. Physical operators are Q closed. We also have an equivalence relation on the space of physical operators, which is that if 2 physical operators differ by a Q exact term, then they're the same. And we also required that the stress tensor is Q exact, and we were able to show that these correlation functions are metric independent. The simple way to ensure that 4 is true, okay, and this is the most common way to ensure that 4 is true, is to use a Lagrangian that is itself Q exact. a Lagrangian density that is itself Q exact. Okay, you can see why that might work. If I have a Lagrangian density that is itself Q exact, then the corresponding action is just this guy, Q commutator with like this guy over here. Okay. Can everybody see why that would work out? It just takes a moment. I'll let you stare at this for a second. If I have a Lagrangian that is itself Q exact, then I'm guaranteed to have a stress tensor that is Q exact, right? Simply because of this. And the nice thing about this kind of presentation, this is the presentation that is very common, commonly used. Is that once we reintroduce factors of H bar, let's reintroduce our factors of H bar. So the Feynman amplitude for a particular transition is e to the I by H bar S. Is that using the same argument that we used to show metric independence of the correlation functions, what we can do is we can show that the correlation functions are independent of H bar. Okay. So in order to convince yourself of this, just think of like taking d by d H bar, like and just writing this out in terms of a path integral. When I act with d by d H bar, what it's going to do is it's going to bring down some guy, but then the guy that it's going to bring down is a Q exact guy, and so the correlation function is going to be 0. Okay. So what this is telling you is that the correlation functions are independent of H bar. Okay. Not only are they metric independent, right, which is what we wanted, what we started out with, but also they are independent of Planck's constant. Okay. Now, what that means is, that's a kind of a nice thing, is what that means. I mean, this is an amazing thing if you think about it. What that means is we can calculate them exactly in classical theory, in the classical theory. There are no quantum corrections. Okay.
Just to ask about the previous thing about the like guaranteed you are constructing this thing. It's just that the stress tensor now takes the desired form, is it?
Yes.
With this, because you are constructing, by construction it's Q slash something with
That's
two
right.
index. Okay.
That's right. So
sorry, maybe I am asking the same question again. This L is Q comma V. This is this does not follow from the previous study. This is you are starting with.
No. So it does not follow from all of this here.
Yeah.
Okay. But what we are saying is that if we want to ensure that property 4 is true, that the stress tensor is Q exact, then we are guaranteed to have that result if we start with a Lagrangian that is itself.
Okay. Yeah, there may be other Lagrangians possible which will give the same Q exactness of the T, but this will definitely give you one.
Oh yes, absolutely. For example, because of what we already know, for example, I can imagine sending V to V plus Q lambda.
Yes.
Okay. And when I send V to V plus Q lambda, we know that Q squares to 0. So the Lagrangian it's not going to make a difference. The stress tensor might pick up some different changes.
Okay.
Right. My point is that if we use a Lagrangian that is Q exact, we're guaranteed to satisfy property 4. That's all.
Sure. Yes. Okay.
To know some okay.
Sorry. No, I'm just saying that like this form of choosing the form of S, how general is it? Like in the sense that can you have some Lagrangian density which is not this but yet, or is there some clever way of seeing that okay, this is the most general thing that you can write?
So I'm not following this question.
No, I'm saying that like this is a choice of S such that you satisfy all this thing.
Yeah.
I'm saying that is this the most general choice, or like or you can have many complicated stuff which eventually leads you to this.
Yeah, I mean, well, I haven't told you what V is, so like there's already a lot of room there, right? I don't know if there is a more general presentation.
Right.
This seems to be the simplest requirement.
Right.
If I have this requirement, then I get what I need. There may be, but I don't know if there is a more general way or a more complicated way of writing.
Okay.
Aditya, you had a question?
No, I just wanted to ask if you know an example where L is not of this form, but somehow something happens which makes
Yeah,
sure
I guess
that.
that was my question also, I think.
L
An
is not
example of L that is not QV.
Oh, okay. So the like the theories that I have seen, L is always QV.
Yeah.
So I don't know. I haven't seen an example where you cannot write the L that. But yeah, I don't want to say something. I don't know. Yeah, fine. I'll say something stupid. It's okay. Like I don't know that a theory that does not satisfy this property is going to be topological. So yeah.
Well, we can't be sure.
Can't be sure. Can't be sure.
Yeah.
But like from all the examples that I've seen, this seems to be a sort
of. Okay.
You idiots, you're just accepting that argument. Do you have any idea how small the number of examples I've seen is? Like,
I know.
Okay, cool. So this is an important point, right? That like the fact that the correlators are independent of H bar, they're independent of quantum correction, which means we can compute them exactly in the classical limit. Okay. In fact, we can evaluate them exactly for any value of H bar. We'll see how that might be useful. Now, what we can do is this bit goes by the name of topological descent. What we can do is we can integrate the defining equation for the stress tensor, which is an equation that tells you that T alpha beta is Q acting on G alpha beta, and we can integrate that along a spatial hypersurface in our QFT, whatever dimension it is, and we can get when we integrate the stress tensor on a spatial hypersurface, then we get the momentum, right? That's the general understanding, right? We get basically that the momentum operator is Q acting on G alpha, some G alpha. Okay. And now what we're going to do is we're going to construct a ladder of operators. Not a ladder of operators, maybe ladder is a bad word. We're going to construct a set of operators, right? So let's start off with the physical operator O. Okay, it's a scalar physical operator, right? So when I say physical operator, I mean that.
Madhu, sorry, can you say what G alpha is again?
G alpha is some guy. What I've done is I've just taken this equation, T alpha beta equals Q G alpha beta, right? And what I've done is I've basically picked the, let's say, the T0 alpha component. I'm doing it in components now, but you can do this in a component independent way. And that's going to give me the momentum density, momentum shear, or something like that. And then I'm going to integrate that along a spatial hypersurface to get the momentum.
Yeah, I want to say something regarding the previous point. This the fact that it's classical and at every H order it's zero. So the explanation you gave is like you just you take a derivative and the action piece comes down. Now if and again, so if that is just independent of the form of the action, I'm just saying then the action has to be of that form, the form that you have written, right? Because whatever comes down has to again give you zero when acted. Yeah,
I understand. So, but the thing is that I understand what you're saying. You're saying that if I require this, right, then S has to be of the form Q acting on something.
Yes.
That's true. Very good. But the thing is that it turns out to be. Okay. Yeah. Maybe one can replace one. I mean, okay. Yeah. Okay. Let me say it like this. Maybe one can replace requirement 4 with a requirement like this. Okay. But I'll tell you why one might not want to do that. The reason one might not want to do that is because this seems like cheating. You're saying that like I want a theory that is defined by a path integral, but that doesn't have quantum corrections, right?
Yeah.
It seems a bit like cheating, right?
Okay.
Whether they are equivalent in the sense that if I assume one, it implies the other, and if I assume the other, it implies completely equivalent in that sense. I have to check, which I can do.
Okay.
But but what we see is that we start off with T alpha beta
Yeah,
like that.
so the defining principle is just this four acting.
Yeah.
The rest of this is probably not more fundamental.
Yeah.
Okay. Thanks.
Cool. So good. So now where are we? Yeah. So we have started with a scalar physical operator, which means that the Q commutator with this operator is 0. And now what I'm going to do is I'm going to act on this guy with G alpha. I'm going to call this O1 alpha. Okay. Now what I will do is I'm going to compute d by dx of O0. Okay. And what d by dx of O0 does is it's basically like this is just a momentum generator, right? Sorry, this is just a momentum. So if I want to compute what this is, I just take the commutator with the momentum generator. Okay. And from above, I saw that from my fourth axiom, I saw that P alpha can be written as Q acting on G alpha, right? And then from this step to this step, what I do is I just use the Jacobi identity, right? So basically, I have Q acting on G here, and what I want is for Q acting on O, because I know that this is true, and I want G acting on O because I've defined this. Okay, so I've just moved things around using Jacobi's identity. I'm sorry for the yeah, I seem to have switched bracket conventions at some point. There's probably a good reason for this. I think it has to do with whether or not with the statistics of the operator. Let's just like don't get hung up on the brackets. Let's just assume that all brackets are graded, right? Which means that you should take into account the statistics of the objects that are being bracketed in order to decide if they're commutators or anti-commutators. What we find is that d by dx acting on O0 is Q acting on O alpha 1, which is the new guy that we defined. Okay. So now what I can do, I can define a one form operator O1, which is O1 alpha dx alpha. Okay. So I'm intuitively, I'm just moving this over here. Okay. And what I see is that do really here means this whole process, where do is just Q acting on O1. Okay. Now the fact that this is a one form means, and this is the goal in life of all one forms. The goal in life of one forms is to find a cycle, pair it up with a cycle, and you can integrate it around. Okay. So what I can do is I can integrate this one form O1 along some closed curve, let's say some closed curve gamma. Okay. But the cool thing is that Q acting on this like integrated operator O1 is 0. Okay. And this is a new non-local physical operator. So the reason it's a physical operator is because Q acting on it is 0. But its support is on some closed curve gamma. Okay.
Yeah, I don't see that. I'm sorry. The Q acting on the integrated one.
Yeah, this is roughly because like so this Q acting on O1 is DO, right? So basically, what that does is
Sure. Yeah, I see it now.
Yeah. So what we've done is we started off with a scalar operator, right? And we had our Q. Okay. And what we've done is we have constructed a one form operator, right? When I say one form operator, what I mean is that it's an operator that takes value. It's a one form worth of operators. Okay. Now I can integrate that along some closed curve, and what I find is that it is also a physical operator, and it's also non-local.
Integration of DO0. I mean, trivially, I will say it's 0, but why cannot it, let's say, have some phase or something when it comes back to it? I mean, when I come back to the same point, I mean, physical operators should not have such phases, but I mean, I do not know what O0 is.
So this is the argument that I'm making here is just Stokes theorem, right? If the gamma is a closed curve, there is no boundary.
Yes.
So if there is no boundary, then you cannot have it's just 0, right?
We see. for this, yeah, see, for integral do, you're saying that we use Stokes theorem. And so
yeah. So so what we can do is similarly we can construct an entire yeah.
Madhu, a question. Sorry. So, but it seems that you're saying that the operator is zero. I mean, the operator itself is zero. Yeah, the integrated operator which you have defined. How? Why was the commutator zero? The bracket zero. I mean, before bracket itself, I think you've made an argument that this integration along a closed curve itself is zero. So the operator you have constructed itself seems to be zero.
How is that what I've done?
Maybe I misunderstood it.
It's small d of something, right? So if you integrate
maybe that's not a good way of thinking about it. Sorry, I'm sorry about this. Maybe the better way of thinking about it is the following. Let's use this notation to refer to this guy. No. Wait, hold on one second. Small d of something.
It's fine, right? What is the issue actually?
Yeah, I'm also not getting the.
Sorry, Advait is confused. Can one of you explain it to me now, please?
No, it seems fine to me because O is an object that makes sense on the whole space. So someone asked why won't we have a phase-like thing? So they are maybe thinking of an angular object.
Right.
Okay, so you have like a d phi where phi runs along a circle. So why can I not have a phase like that?
Right.
The answer to that is that, well, phi does not make sense as a smooth object on the whole space.
On the whole space. Yeah.
Okay, but here you're starting with O naught, which itself makes sense on the whole space smoothly.
Right.
And you have a d of that. And if you now integrate that on a loop with no ends, that will vanish, right? Because it's d of something.
Yeah. I had a very stupid confusion. I thought that integrated O1 is the new operator we have constructed. Sorry. It's just
so you do the integral on the two sides of that equation, and you get the next one from that.
Yeah. Sorry.
Yeah, my question was wrong.
Sorry. No, I should have said that clearer, perhaps. Yeah. Right. So the new operator. So just to clarify, this step is telling us that the new operator that we have constructed is a physical operator. Okay, but the new operator itself is perhaps better represented by the left-hand side of this guy, right? That O1 is the new operator, right? And like Aditya said, when we take the integral on both sides, then we get this. Okay.
I forgot what O1 was. Can you
Sorry, O1 is
write that on the side? No.
Oh, O1 in terms
of the sense that how did we start it? Oh yes, exactly.
We took a commutator with G.
Okay.
Yeah. So the point is that we can keep doing this. In fact, you can do this higher and higher. Okay. So we started off with just O being a physical operator, O0 being a physical operator, right? Then we have an O1, right? Which we constructed as just one G acting on O0. Sorry, G acting on O0. Right? If I can do this again, and then I get like an O2, and all the way, and so O2 is going to be a two-form operator, right? O3 is going to be a three-form, and so on, all the way up to On, where n is an n-form operator. It's a top form in the sense that I'm assuming that the dimension of the manifold that I'm working on is n. Okay. And obviously, the next step over here, which is DON, is 0 because you don't have any n+1 forms. Okay.
Sorry, can you repeat this tower? Why do you have two forms? Sorry, can you show the previous equation one?
So I have constructed. I constructed O with what you want to see. I'm trying to.
Yeah. I mean, I thought the reason why you have this one form was because of integrating over a spatial slice. and then you got this G alpha, and from there, so how do you get these two forms and so on?
Well, you just keep acting with more G's, right?
I see. Okay.
Yeah.
Okay.
And yeah, you just keep acting with more G's, and you will get like the higher forms. So that's the sort of the point, that there is a sort of you use the Q operator to construct a tower of P-form operators, each of which is physical, right? So it's a new class of operators, right? And this construction, of course, terminates because there are no n+1 forms. And by the same argument, integral OP over a p-dimensional submanifold is zero, right? Is this. Okay. Now the interesting thing, the reason that this is kind of an interesting thing to do is that you know, this in particular here, what I've done is I've written this out for the top form, the ON. Okay. And the reason this is a cool thing to do is because the top form is integrated on the whole manifold. It's not a submanifold or anything. We're integrating it on the whole manifold. What that means is we can add deformations, let's say T alpha, ON alpha, to our Lagrangian without spoiling the topological nature of the theory. Okay. And further, using the argument, the argument about the H bar dependence, right? I can consider derivatives with respect to the TAs, because these are now some moduli. Okay, these are now some parameters in our problem, right? And what we will find is that they are not sensitive to the values of these guys. So this is a very powerful thing, because basically it's telling you that you can add stuff to your Lagrangian, right? You can add top forms, and maybe adding those top forms will allow you to make some clever rearrangements. But none of these deformations affect the topological nature of the theory. These deformations protect the topological nature of the theory.
Here, this ON is not Q exact, right?
ON is not Q exact. Hold on. ON is not Q exact. No.
In the sense that ON is not Q something.
Q something. Yeah. Right.
Yeah. So this fact that you said that you can, what you did with H bar, you can do with the T that sits in front of an ON. I don't quite see why that would be true, because ON is not Q exact.
Sorry. Yeah. No. You're right. I got carried away. No. Yeah, that's right. But the point is that when we have these, that's absolutely correct.
But if you add to the action, you will have that integration also, right? Over the manifold.
You'll have the integration over the manifold, but the argument that I mentioned earlier about taking the derivative with respect to H bar and pulling something down, if whatever you pull down is not Q exact, then it's not. Then you're not going to be able to argue that.
Well, for the action, it is right.
Well, sorry, go on.
ON is not Q exact, but the integral of ON over the entire manifold is Q exact, right? That's the equation.
Yeah, that's why.
And that's all you need to show that the deformation doesn't change the action.
Sorry, why do you say that the integral over M is Q exact?
It's written on the screen.
It's written.
This equation.
No, but
no, sorry. It's Q closed,
is not what
right?
Q exact means.
It's only Q closed.
No. Okay, there's two different statements. Sorry, let me just try and clarify. And if I am not able to, then you jump in. Okay. So there are two different statements. Okay. The first statement is that you know, the integral of integral of ON over the manifold is when you take the commutator with Q, it's 0. Okay. What this tells you is that the deformations do not spoil the topological nature of the theory. What Aditya is saying is a different thing, which is that ON itself is not Q of something, which is true, right?
Sure,
that's what I was saying. Yeah.
But sorry,
Madhu, can you elaborate on what you mean by when you add deformations, it won't spoil the topological nature? I mean, are you adding into the Lagrangian L plus TA OA, or you're adding something else?
I'm adding terms like this.
This A counts what? This how many operators you can have, or It is not a space-time index, right?
No. A is not a space-time. A is just basically like T1.
Okay.
And so on.
Okay.
Like I was thinking that you will add it like in the Lagrangian in the way like S is equal to commutated Q in the V basically. You are not adding it in the V. You are adding it like separately.
Yeah, that's my question.
Yeah.
Okay.
Yeah, you're adding it separately. You're not adding it to the V. Because there's no guarantee that ON itself can be written as Q of something, right? Which means it may not be possible to write it. But basically, what this construction is telling us is that there is a class of deformations, right? The fact that we can construct.
So we are adding this to the Lagrangian, right? So the action is changed by integration of this over the manifold. So automatically, I think what people are saying, it's all consistent, right? Because when we differentiate with respect to h bar, we are pulling down the integral of ON, and therefore which is Q closed, right? So,
but you need Q exactness for that.
Okay.
You need the guy that comes down. Sorry, I made an incorrect statement. I should apologize. Which I will apologize. I am sorry. No, it's what we're saying is that the guy that comes down has to be Q something, and then the right. Okay. Now I should not have said that. The point here is that there is a class of deformations we can add to our Lagrangian. This is going to be of some use in the future. And in fact, what we will do is maybe much later on, after we have introduced supersymmetry and all of that, we'll explicitly construct these operators. Right.
So then, like the last thing that about D of D H bar, that condition is not true now after adding this deformation, right?
D H bar.
Like D H bar of the correlator is equal to 0. That is broken by adding deformations of this type, right?
I think so. I think what one would do is that you have the 1 over h bar s.
Yeah.
You hold that and you add the integral over ON extra to that. So it's not like you're adding it to the S and the h bar is outside. So you have the 1 over h bar s, which is the Q exact object.
I see. I understand. Okay.
Right.
So you don't add with any h bar.
The h bar just comes with the Q exact action.
Piece.
That's all.
I see. Okay. Fine. Got it.
Can you say that again?
Sorry.
Can someone say this again? I can follow this.
The addition of these deformations, right, is separate from the h bar stuff that's happening. Okay. That's all that. So these two facts, they don't talk to each other.
Okay.
Maybe you could write it. I mean.
Yeah, but you're saying you're adding these deformations to our Lagrangian. If you had said our action, maybe it's just language, which is.
Yeah, should I have said action?
I mean,
also, if you say action, then also it will be a. But yeah, as you said, it is clear. But
one point is that in the initial you made the statement that all examples are of the form Q, V for the Lagrangian. But if the minute you add this deformation, it is no longer of that form. And my understanding was that the d by d h bar of the correlation function being 0 was a consequence of that form of the Lagrangian and the action. And since that is no longer true, I don't think we should. I mean, this is also true anymore, right? I mean, if you of course add it without h bar,
that's what I was saying. Yeah. So you just keep the h bar piece with the Q exact part of the action. And then you can move that h bar to make it as large as you like or as small as you like.
Right. But, so what you're saying is that I will still have that property, which is d by dh bar of the correlation function being 0.
That is right.
L is no longer Q close. L is no longer Q exact. L is Q close, but no longer Q exact.
Yeah. This strategy where you can make that object, you can say it's h bar, you can say it's t, the object that sits in front of the Q exact part of the action, you can make that as large as you like or as small as you like, but you can only do it for the part which is Q exact, not for anything else.
And so this is going to be useful because, for example, sometimes we write down a theory where we will have like, what we had said earlier, which is that there's a Q exact piece multiplying a 1 over h bar. Okay. And then I'm going to add something else. And now what I'm going to say is that I want to study this theory at like really small h bar, right? And what that does is that tells me that like that tells me which of these, I mean, depending on where I send h bar, that tells me which of these terms is going to dominate. And that allows me to play further games, with the path integral itself. And this will be useful. This is useful, for example, in studies of localization and stuff like that. These sort of techniques are used very commonly.
Yeah, the entire formalism seems very reminiscent of the things that happens in localization.
Yeah. In fact,
it's the same thing.
It's the same. It's literally the same thing. Yeah. So yeah, it's just
there
that
also
in the local
Q exact part to the action, isn't it? You add the Q exact part.
Yeah. So the point is that the only thing is that in the localization studies, typically from the get-go, we start off with a theory where this Q here is basically some supersymmetry. Okay. Of the theory. And here I'm not saying that I need supersymmetry or anything like that, right? Although the examples that I will work out in the future will be supersymmetric theories, because those are the nicest places that this sort of thing can be seen very explicitly. So all of this seems quite abstract, right? But hopefully you're getting a sense of like the sort of general properties. And the goal is to actually build examples of these theories. Okay. And what I'm going to do is I'm going to try and build examples in lower dimensional quantum field theories. I'm going to look at 0, 1, 2-dimensional quantum field theories, right? Which is just, supersymmetric quantum mechanics and sigma models and stuff like that, right? Because those are nice examples, very nice playgrounds. And in order to do all of this, we'll need to sort of brush up on some geometry. So this is a sort of pause point for questions if there are any. If there aren't, then we can move on. So are there any questions?
So I had one question, sir, because I forgot the starting of the lecture. So you say that we add these deformations without spoiling the topological nature. So the topological nature of the theory was like when we differentiate it with respect to the metric, the correlators will be 0. So what is the condition for that? Right. Can you just show that condition once again? Or just reiterate what it is? Maybe not show.
When I say that a theory is topological, I mean that its correlation functions are not dependent on
the metric. Yeah. Metric. So then what was the calculation here? So Q, G, alpha, beta is equal to 0. Okay. And so, so the condition there is that this Q with the integral of ON, this N form thing is 0, and that is why you are saying it's topological exact. Yeah, it's topologically invariant when we add that term. I mean, these are two separate things, right? Saying that it's invariant under H bar and saying that it's topologically invariant. I want to make that clear. Like, these are two separate things, right? I don't understand that. I mean, topologically invariant was saying that it's invariant under the metric. Then you introduce this H bar thing. So I'm just confused.
Right. There is so I don't have a clear answer. Maybe someone who can say this better can say it. But it's typically a question of how you're approaching the problem. But there is some interplay between these two questions. So, for example, if we start off by if this was a series of lectures on localization, right? I would say that my goal is to study systems where the saddle point approximation is exact. Okay. And what I mean by that in a quantum mechanical or quantum field theoretic sense is that my classical answer is the full answer. Okay. And over there also you have arguments like this.
Yes.
Very like almost the same arguments essentially. So I don't know. Maybe Aditya, do you want to say something that might help clarify this?
I think the first thing that he asked, whether this equation that you see right now on the screen, does this mean that it is topological? The answer to that is yes, because I mean, as physicists, we use these two words to mean the same thing.
Right.
The equation about the H bar is something additional. It's a bit extra, which, you know, had you not picked an action which was Q exact, that statement would not have, you know, been valid. So that is like an extra statement which often we should expect will happen, because often the actions we study are going to be Q exact,
right,
or will have some Q exact part in the action.
Right.
But I would say that the answer to what he first asked, whether this del by del H alpha beta of some wave vanishing, whether that means that it is topological, I would say the answer is yes, isn't it?
Right, absolutely. I think the thing that he asked after that was, is the statement that d by d h bar acting on the correlation function is 0 and del by del h alpha beta acting on the correlation function is 0, are these two synonymous?
Tushar, I don't think no. I don't think that statement is right, because that was true only because we assume that S has Q exact. I mean, S is Q exact.
Right.
What can also happen is that the statement that you're seeing on your screen right now is not valid, but the action has a Q exact part in it.
Right.
Sorry, I
where too you could do the same thing, where you could do a d by d.
Right.
But the derivation of the screen comes from this fourth assumption, right? That the stress tensor is Q exact.
Yes.
So the action.
Yes. Stress. Yes.
So the action, if action is Q exact, then the stress tensor is Q exact is just obvious. But I'm saying I think the axiom is that the stress tensor has to be Q exact. So then the derivation just follows whatever is on the screen.
Yes.
But I'm a bit confused now. If S phi, you add to S phi the terms that you just TA O in A, right?
Yeah.
Then will this condition hold true? Because I would have thought that you won't get something like Q anti-commutated with some two indexed object here from that part of the addition to the action, right? Like for example, like take S prime phi is equal to S phi plus TA ON A.
Right.
Integral over M.
So let me just write that.
So now we'll again with this thing, as you said, that the addition of such a thing makes sure that this is topological, remains topological. I can see this from the H bar argument, because H bar is just S is Q exact, and with an H bar coming in front, the other one goes for the right. But this one, can you is it obvious? Because there is an integral over a manifold in this part also. I would.
But you don't have an H alpha beta.
Okay. So you are saying that
you have you have an n form. I mean, you do integral over the n form.
Right.
You have not used the H alpha beta.
Okay.
You should really think of this as like a deformation.
Right.
The standard way in which we talk about deformations of quantum field theories. Right?
You had no hot star. You had no square root of H. You didn't have any of those structures which would make use of this. So it's fine.
Okay. Sorry.
But the statement about the d by dh, just that is a whole separate thing, which holds if your action has a Q exact bit in it. But that is kind of loosely linked to this. But yeah, it's a loose link.
Yeah. Tushar, is that okay?
Yeah. Thank you.
Cool. Okay. Any other questions? Okay. So this sort of ends the sort of physics part of this talk, and it looks like I'm already doing very badly on time. But what I want to ask at this point, before we continue, or if we continue, is this pace too slow? Because if it is, I can try and prepare better, and then I don't have to spend that much time saying things incorrectly and then correcting myself. I'll prepare better nonetheless, but please tell me now if this pace is okay.
For me, this is very okay.
Yeah, I think this is good.
Excellent.
Okay, maybe can we do polls in this? Never mind, it's okay. Sorry, so I should ask the organizers then, guys, there's 10 minutes left. So what should I do? Original plan was 11 o'clock, right?
Right, original plan was 11 o'clock. How much more material, roughly?
Oh, not even go there. I sent these guys an email. I said, in today's talk, I'm going to do all of this. Then I'm going to talk about fiber bundles, then connections on fiber bundles, and then characteristic classes.
All of this today.
No, then the plan changed to just fiber bundles and connections on fiber bundles. But now it looks like even the fiber bundles starting will be a bit difficult. So you guys tell me what to do.
So maybe we can ask the audience if people want, let's say, are okay with. So we have 10 more minutes. So if, let's say, another 30 minutes from now, so basically an additional 20 minutes, if the audience are okay, can you please raise your hands or something? If
it is late though, so
go.
Please don't.
There is enough number of raised hands, then we can go ahead, maybe.
Please vote.
We have to raise hands if you are fine with him speaking more.
Yes.
Aditya, I'm looking at you. Oh, you raised it. All right, good. This guy with his video on and he's not voting yes, it's quite a slap in the face. Okay, I think maybe we can continue next time.
Yeah, I have to go eat, man. Dinner.
Yeah. Okay, maybe let me just take. Okay, so since I have maybe 10 minutes, right? Let me just introduce the notion of a fiber bundle, and then we can sort of pick up from there and continue. Is that okay? Guys, is that okay?
Yeah.
Okay. Cool. Cool. So I'm going to assume that you're familiar with manifolds, differential forms, and Riemannian geometry at the level at which we typically are comfortable with our work in general relativity. So the goal of this section is to really talk about fiber bundles, connections on fiber bundles, and characteristic classes. In particular, to sort of try and be of use not just to my own lectures, but also Shubham's lectures, where he will use the notion of a characteristic class very heavily to construct these things called anomaly polynomials. So it will be kind of useful for us. So just to get a sense of how, if you have seen this stuff before, can you just raise your hands just so that I have a sense of what I'm working with? Okay, so there's a few people. Okay, cool. So good. So anyway, I guess this is, since you guys said that the space is okay, we can move through this stuff at the space, right? So the notion of a fiber bundle is very useful in physics. It shows up in a lot of places. What we're going to do is we're basically going to take the idea of products. So in the case of Riemannian geometry, what we do is we start off with the idea of a space, and then we say that it is locally flat, but globally it might be curved. Okay, that's the basic idea. Local flatness, right? Because locally you can always find a neighborhood where you can set up a coordinate chart and you can have an isomorphism with Rn or Cn or something like that. Right? In the case of fiber bundles, what we're going to do is we're going to perform the same kind of transition from local to global, but the object that we're going to be looking at is the product structure of a manifold. Okay, so the idea is roughly that for fiber bundles are locally like products, but globally they might have some non-trivial topology. Okay, so if you sit in a small neighborhood, So let's just just follow this. So we have a manifold M, which we're going to call the base manifold, and we have another manifold F, which we're going to call the fiber. Okay. So what we typically say, we typically say that we have a fiber bundle E over M, right? That's why we call M the base, and it has a fiber F, and locally it is a direct product of M and F. That means if I look at the manifold, and then in a small neighborhood, right over here, this guy is going to look like UI times F, where UI is some local coordinate chart on M. Okay. So for a manifold M with, let's say, some atlas U, so a collection of charts, like UI, E is in each of the chart, it is simply UI times F. Okay, so this is the manifold M. We have some chart, and I'm denoting the fibers by these vertical lines over here. Okay. Locally, the idea is that it is UI times F. Okay. Now the point is that just because it's locally a direct product, that does not mean that that does not mean that globally it is also the case, right? The fact that it is locally a product does not specify global topology. What we have to do is, when we define our manifold, in order for this this notion of a bundle to be non-trivial, what we have to do is you have to tell me what happens when I move from UI to some other UJ. Okay, and that's going to happen through what are called transition functions. Transition functions are the analogs of when you're studying ordinary Riemannian geometry. Then you have overlaps of coordinate charts, right? And in the overlap region, your maps, your isomorphisms with Rn or Cn, they have to satisfy they have to satisfy certain properties, right? These are the same kinds of properties that we require. Transition functions tell us how the fiber manifolds match up in the overlap regions. So if I have let's say some UI and some UJ, and they overlap in some region, right? Then I have these functions, they're called transition functions, which basically are maps from the fiber at UI to the fiber at UJ in the intersection region UI of UI and UJ. Okay. So the whole theme is that this is a locally trivial object, but globally it might be non-trivial. And the simplest example that one can think of is like a Mobius strip, right? So the Mobius, in the case of the Mobius strip, the base manifold is just a circle. It's just an S1, right? So I just have a circle, and the fiber over the base manifold is just let's say the unit interval, okay, 0 to 1 or minus 1 to 1, whatever. Now the point is that locally, if I look at a small region, right, then I'm just going to have S1 times this thing, S1 times minus 1 to 1, okay. But the point is that I can patch these guys up in multiple ways. What I can do is I can construct a band, and a band is just having the minus 1, 1 with the same orientation all the way around, right? So I just have this kind of band. Okay? The other thing that I can do is in the overlap regions, in one of the overlap regions, I can flip things around. Okay. And so basically the way the coordinates are related to each other, instead of, let's say, the coordinate t is let's say the coordinate t is in minus 1 to plus 1. What I can do is I can relate for it to be trivial, for it to be just a band, I can relate t1 to t2. Let's say where 1 and 2 are the two regions on like an S1. I cover the S1 with like two charts, and I just say that T1 is equal to T2. The other option is I can make the identification T1 equals minus T2. And then I get like that's basically what flips me around, right? And that's what gives you the construction of the Mobius strip. Okay. We can also have what are called trivial bundles, right? Trivial bundles are not very interesting. They're so a trivial bundle just means that it's globally just a product, M times F. And in this case, like all the transition functions are just identical. There's nothing interesting happening when we're moving from one patch to another patch. Okay. It's a theorem that I won't prove this, but one can prove it, that any fiber bundle over a contractible base, right? A contractible manifold is, let's say, like if I have Rn, for example, I can move all of the points down to a single point. Or if I have an n sphere with one point removed. If I have an n sphere with one point removed, I can imagine just shrinking the sphere along the sides and then having it shrink to a point, right? So a contractible, if you have a fiber bundle over a contractible base, then it is trivial. So typically, a base manifold must have a non-trivial topology in order for you to have a non-trivial fiber bundle. Okay. Is everybody clear on what the idea of a fiber bundle is?
So this statement is independent of the kind of fiber you're studying.
Yeah.
Okay.
And the way that we'll see the proof, like the way that one proves this is, you sort of use homotopy, right? And we'll see where that how that comes in. But is everybody clear on what the idea of a fiber bundle is? That locally it's a product, and globally it might be some non-trivial patchwork. Okay, cool. I think my time is up. I can maybe define what a section is, or maybe we can stop here. There's no natural point to once. Let me just see. Okay. Let me just finish this page. Okay. We'll define everything formally, but a section, right? So we have defined a fiber bundle. So we have a base manifold, we have a fiber, and we have the full sort of bundle. A section of E is our fiber bundle. What it does is it assigns a point S of X, right? S of X is in the fiber F, right? For every X that's on the base manifold. So what section does is it basically takes you associates to each point in the base manifold. It associates a point in the fiber. Okay. So you can think of this as like a sort of, I mean, I'm just saying this in words. You can think of it as like a function living on the fiber. Okay. This is not a good thing to say out loud, but it's okay to have it in your head. Okay. So for example, in this image, this is what's indicated, that S of X is basically just an assignment of some values in the fiber corresponding to points on the base manifold. Okay. And like we are building up to a sort of formal definition of a fiber bundle. Typically, it involves the definition of what's called a projection operator. Okay. Sorry, I mentioned that a section assigns a point S of X on F for every this thing. Local sections are defined on patches, not on the whole manifold. Okay. So typically we start off by defining our sections locally, and then we try and piece them together. So a projection pi, right, is basically a map from the fiber bundle down to the base manifold. Okay. It's not a map from the fiber to the base manifold. It's a map from the bundle to the base manifold. And what it does is it basically the projection. So E is locally. Let's write this. E. So E in some patch is just locally UI times F, right? So what a projector does, projection pi, it just picks out the first guy in this product. Just gives this. Okay. So locally you have like a product, and what a projector is doing is it's saying that forget about the fact that there is a fiber, just focus on the base manifold. Okay. And in this way of writing things, it's easy to see that the inverse image of a point, on the base manifold under the projector pi is the fiber over the manifold itself. Okay. When I say inverse image, what I mean is all of the points that in E that if I act with pi, it's basically identity, right? That is precisely what the fiber over X is. Okay. So what I'm doing is I'm basically I'm not defining. I'm trying to define the fiber in terms of the projection. I'm not saying that there is a fiber separately. I'm saying that I just have a base manifold, and I have a bundle over a base manifold, and I have a projector. And this is how, in this way, I'm able to define what the fiber is. Okay. So for some neighborhood of some point UI, you consider pi inverse of UI, which is the inverse image of all of the points in UI under the projector pi. That subset of E, so that is the subset of E which projects down to UI and M. In order for this to be a fiber bundle, we basically require that there exists an isomorphism relation between UI tensor F and pi inverse of UI. Okay, is this clear? This is an important, I mean, it's kind of the important part of the definition, right? That I start off with I have a base manifold and I have a projector which maps from the fiber bundle onto the base manifold. Okay, so what I do is I look at a small region, a small neighborhood on the base manifold, and I ask what are all the points in E that when I project using pi bring me into this small neighborhood. Okay, and the definition of the fiber bundle is that it involves an isomorphism relation between this inverse image pi inverse ui and ui tensor f, ui product f. Okay. Now this is what is called a local trivialization. Okay, this is analogous to local flatness. It's a local trivialization in the sense that the global non-trivial fiber bundle product is now rendered trivial because of this isomorphism. Okay, so when I say that we have with a local trivialization, what I mean is that locally in some patch I'm able to write down an isomorphism. I think maybe we can stop here, but like if there are any questions about this, I can answer.
So whenever we see pi inverse of ui, we can just think of it as ui cross f, right?
Yeah, because there is an isomorphism. Yeah. Okay. But
and this isomorphism need not be the same for all ui. It might be different, but that is still fine. Or
well, I mean, okay, I understand what you're saying. So you're saying basically that if I have like an overlap or something like that, what do I do?
Yeah.
Right. We'll see that. Yeah. We'll see that, like, the whole idea of like transition functions that we alluded to. We'll define them formally in the next class.
Okay.
This might seem a bit, I don't know, this might seem a bit roundabout, right? But mathematicians have established that this is like the best way to phrase the whole conversation, and we trust their kind of their characterization of the subject. It's very productive, right?
So the existence of this isomorphism is a part of definition of this fiber bundle.
Yes.
Isomorphisms and the transition functions, both, right?
Yeah. So okay. So let's see what each of these guys do. Okay. The transition functions tell us how the fibers on different parts of the base manifold are related to each other. Okay. So the transition functions are in some sense related to how the product is twisted. Okay. Fiber bundles are also called twisted products. So the transition functions are kind of telling you how the products are twisted. Okay, you'll remember that it was the transition functions that told us that the Mobius strip where something funny is happening versus where the band where everything is simple, right? So the transition functions are keeping track of how the fibers are related as we move along the manifold. Okay, what the local trivialization, what the isomorphism is telling you is that the isomorphism is really telling you what the fiber is in some sense. Okay, so from this point, right? So I told you earlier that there is a fiber and all of that. Okay, but what I can do is I can start off my definition with just some. Where is my? Yeah, I can just start off the definition with some space E, right? Defined with a projector onto M, right? And this starting point, along with the requirement of this isomorphism, is enough to tell me that there is an F, because this isomorphism is basically telling me what F is, right?
Yeah.
So it's really a question of like how we formulate it. I'll show you the definition, right? So a fiber bundle E with fiber F over M is a topological space E with a projector pi which maps E to M that is locally trivial, which means that for all X in M, right, for all points on the base manifold, there exists a neighborhood UI around it that contains X and an isomorphism phi I, which maps UI tensor UI times F to pi inverse U, such that if I start off with, let's say I start off with, phi I maps ui times f into pi inverse u. Okay, so if I want to act phi I on something, it's going to act on something that looks like this, right? This guy, an element of this set is going to look like this, right? That's what I've written here. When I act with the phi I, what that does is that takes me into pi inverse ui. And then when I act on that with a pi, I just get back x, right? Because what the projector does is it says, forget about the phi, but just give me the first value. Okay. So that's the what's it called? The formal definition. Are there any other questions?
So the torus, let's say T2, which you write as S1 cross S1, is that an example of non-trivial fiber bundle? There is no twisting or so.
Yeah,
No, it's not.
There's no non-trivial product. So yeah, it's not.
If it has the structure of F times M, then
yeah.
It's not.
So T2 is globally S1 times S1, right? Basically, at every point on one circle, there is another circle. So it's not.
So there should be some twisting, some non-trivial transition function sort of.
Yeah. For it to be a non-trivial fiber bundle, yes. What you would say the torus is a trivial bundle.
Okay.
So when base is non-trivial, doesn't always mean fiber bundle is non-trivial.
When the base has non-trivial topology,
doesn't always mean that the fiber bundle is non-trivial.
Yes, that's right. That's right.
No, I mean you could have a cylinder, right? The base is, I mean, you could have a cylinder which is trivial S1 cross R.
No. What he said, if I understand correctly, what he said was just because the base is non-trivial, that does not mean that the fiber bundle above it is necessarily non-trivial.
Yes,
right?
Yes. But I think what he said was that.
Oh, no, this is what I'm saying.
Okay.
Yeah. Are there any other questions?
Sorry, one small question.
Sure.
So the information of fiber bundle is F, phi I, and the transition functions. These four objects.
Yeah, that's a good question. I would say that E, pi, and what else do I need? And phi. Sorry, yeah, E, pi, M, and phi. I would say that's what you need.
And you want the transition function?
Madhu, so once you define E, the whole fiber bundle itself as a manifold, phi comes up, phi is in the definition of the manifold, the transition function. But phi.
Sorry.
No,
Advait, once you broke up, I couldn't hear that.
Hello. Yeah. So I'm saying that we're defining fiber bundle E as something that locally looks as a product of B and F, right? And
M and F.
M and F, sorry. M and F. And what this local structure is defined by pi. So all of these four are in the definition of fiber bundle. Is that correct?
I mean, okay, you're asking me formally, I would say that there is E, pi, M, and F, phi, right?
Cool. Yeah.
Right, because in order to define phi, I need to tell you what F is. So, if I tell you these four guys, I think that should do it. But maybe I'm being too quick.
The information in phi and F can be exchanged.
Yeah, I would.
Yeah. So I get your point.
But I mean, just because I know that the phi, see, the thing is that the reason that phi I, I'm emphasizing this is because the phi i's are really the guys that tell you how the fibers on different base charts, base neighborhoods are related to each other. So they really capture all of the information about the twisting of the bundle.
Yeah, I think just to add to what he was asking, so the thing is to get F, just F, if you just want to know what the set F is, you would just act pi in inverse on some small x on the base space. let's say if your issue was how do I extract what f is, what the set f is, you just start pi inverse on some small x in M, and that immediately hands you what your fiber f is. Phi I will do something more than that actually.
Yeah. Phi I is really telling you not just f, but also how the f here and the f here are kind of like related to each other. So
yeah, so this is the thing I'm confused with. I'm just saying that if you know E as a manifold, you already know transition functions, right? And if you already know transition functions, then won't it always just tell you how neighborhoods are how do you go from one neighborhood to other neighborhood? It's what you
no. So
I mean, there's something, yeah.
So yeah, what we're thinking of E, we're thinking of E not as a not necessarily as a manifold. See, the thing is that we're thinking of it as a topological. The reason I'm saying this is because later on, what we will want to do is we'll want to say that F is some vector space, or F is some Lie group. Okay.
Oh, I see. Sorry, that's
so,
yeah. Okay.
So the idea that just because I know E, I already have the transition functions of it as a manifold that's not sufficient, because really the fact that we have fibers here is telling us that we need to specify how the fibers in different patches are related to each other, and that's the role that the transition functions play.
Can I add to that? So I mean, even if you knew E as a manifold, if you want to work with quantities intrinsic on E, none of this is necessary. I mean, you could, like you said, E is a manifold, so you know all the transition functions, and you could work with vector fields on E. But usually there are applications where you don't want to know you don't want to work with geometric objects on E, but you want to work with geometric objects defined on M. And if you want to work with objects defined only on M and try to describe everything in E, then you need this phi I. So, I mean, for example, in gauge series, if the gauge field a mu, that is a quantity that is defined on the base space. You don't define it on the full bundle in that sense, right? So, if you want to use quantities only defined on M, then this language of fibrometals is useful. If you have access to geometric quantities on E, then this is not necessary.
Okay, thanks.
Yeah. Are there any other questions?
Okay, then I think then we can thank Madhu for the very nice lecture, and I will stop recording.